All right, we've been talking about different kinds of lines associated with curves, secants and tangents in particular, but I also want to include something called a normal line or an orthogonal line as well. That's in this lesson. So let's say we've got a curve, some function f of x. Okay, a secant is defined as a line containing two of the points on the function. So here's 2 points on the function, and the line drawn through the 2 points, straight line drawn through the 2 points, is a secant line. Okay. And we've been approximating something called a tangent line. A tangent line is a line that just touches the curve once. Right? Now, by the way, this is in the local region, so the function could double back and it could touch it elsewhere, but it touches it just once in this space. This is called a tangent line. Okay? And a normal line, a line that is normal to the curve at the point, is a perpendicular line. So a normal line is also called an orthogonal line. Normal and orthogonal basically mean the same thing. Is a line that is perpendicular, okay, to the line. So when you find the tangent line slope, the normal is the negative reciprocal. Just to remind yourself, if we have one slope, the perpendicular to that is -1 over that slope, okay, or in 1 over m1. So, in other words, if we have a slope of 2/3, perpendicular slope is -3/2. Okay, just a little bit of algebra review. You're going to need that. Okay, so let's analyze this a little bit with Desmos. I'm going to see if I can take you step by step through the ideas behind this in Desmos here. Let's say I have some function. Okay. I have some function y equals x cubed. Okay, and I'm interested in the slope at 0.2. 0.2. So 0.2, the output would be 0.2 cubed. Okay, so that's a point on the curve. I'm interested in the slope of the line tangent at that point. Okay, and let's zoom in a little bit here, change the window just a little bit. So we'll go y-axis from 0 to 0.1. Okay, there we go. That'll give us a good picture of it here. All right, so we're interested in the slope of the tangent line at that point. Now, one possibility is I take something a little bigger, right? A little bigger. Let's say 0.3, right? Go 1/10 to the right. 0.3, output 0.3 cubed. Okay, and there's our line, right? And I'm going to find the slope of that line, right? The slope of that line is, I'm going to do m equals here for slope. M equals the change in y, 0.3 cubed, minus 0.2 cubed, all over 0.3 minus 0.2. Okay, and there's our slope, right? And I can verify that that's the correct slope. I can verify that's the correct slope, and actually, oh, 0.2 cubed. I was trying to figure out why it was negative. Okay, because it shouldn't be negative. All right, so there we go. I had a squared instead of a cube. All right, so let's graph the line. Remember the point slope formula of a line? This is what I'm going to use here, and you need to be familiar with this. Y minus the y value equals the slope x minus the x value, right? That's the point slope form of a line, right? So let's do that here. I'm going to use 0.2 and 0.2 cubed as my point. So y minus the y value, 0.2 cubed, equals m, and I've already got m's defined, so got that. X minus the x value is 0.2. Okay, and there we go. There we go. We've found the slope of the secant line. Now, is that going to be approximately the slope of the tangent line? And you can see as we zoom in here that it's too steep. It's too steep. Now, I can make a better estimate here by putting in something other than 0.3, like 0.21 and 0.21 cubed, and do those really close, right? 0.21 cubed, 0.21, right? And then we get something a little bit better, but it's not perfect. If we look at it really closely, we'll notice it's still a little bit too steep, right? It's still a little bit too steep. So what we're going to do here is we're going to change things around. What if I make a slider? What if I put in, instead of 0.21, I put in some number a. Some number a, and I'm going to put in some number a cubed here. Okay, and I'm going to add a slider for a, right? But this is going to become a cubed. And this is going to become a, right? And we're going to add a slider for a here. And a is going to be values from 0.2 to 0.3. Okay? Step size. Okay. All right, so now we've got a situation where I can grab those values of a and I can vary them. I can shrink them down, right? And let a get smaller and smaller and smaller and smaller and smaller, right? And you can see my slope values are changing as I get. So as I get smaller and smaller and smaller, I get closer and closer and closer to the slope of that tangent line, 0.12, right? And if I get right on top of it, if I get down to 2, I get no line at all because we have just created an undefined slope. But if I let it be just a little bit bigger, like 0.2006, I get a slope, right? So here's the concept. We're going to take this second point and move it closer and closer and closer to the value, the x value that we're interested in. Okay. Now let's change things around a little bit here, and let's say let's take, instead of 0.2, let me get rid of the a slider here. Instead of 0.2 or 0.23, I'm going to do this. I'm going to do instead of a, in other words, I'm going to do 0.2, 0.2 and a little bit more. 0.2 and a little bit more. So 0.2 plus h, right? Okay, this then becomes 0.2 plus h quantity cubed, right? And I need to add a slider for h now. Now h is the difference, how much difference space, the horizontal space, there's going to be between 0.2 and the value I'm interested in. So I'm going to let h vary from 0 to 0.1. Okay, and there we go. We get our slider, right? Now, of course, I'm not using a. I'm using 0.2, 0.2 plus h cubed, and I'm using 0.2 plus h. Okay. We have the same situation now. We've got, only now the slider is not for the x value. The slider is for how much I'm increasing the x value by, x plus h or a plus h or 0.2 plus h. And again, we have this same situation. As the distance between, as the x distance goes to 0, as it goes to 0, we get closer and closer to the limit, right? So that's a nice little demonstration in Desmos. But let's write out formally what we've just done here. Okay, we just said if we want to find the slope of the tangent line, I'll use m for now. Later on, we're going to redefine it as a derivative. So the slope of the tangent line, is the limit as h goes to 0, okay, of f of, the limit of f of a plus h, okay, f of a plus h plus, or minus f of a. So there's that change in y, that subtraction that goes on for the y's, y2 minus y1 over x2 minus x1. So a plus h minus a. Now notice the a's actually cancel out, and this just becomes h. Okay, so this is the definition of the limit of a, or of the slope of a tangent line, right? So the limit as h goes to 0. So let's apply it here. Let's apply it to something simple, fairly simple here. Let's say f of x, let's do our problem. F of x equals x cubed. And we're going to find the slope of the tangent line, at x equals 0.2. Okay, using kind of funky notation here. So here's what I'm going to do. I'm going to find the limit as h goes to 0 of f of 0.2 plus h minus f of 0.2 all over h. Okay, and let's do the algebra. The limit as h goes to 0, f of 0.2 plus h, f of x is x cubed, so 0.2 plus h cubed minus 0.2 cubed, 0.2 cubed. Got to be really careful not to make a mistake here. All over h. Okay, let's cube this thing. 0.2 to the third power is 0.008. 0.008. Plus 3 times 0.2 squared, 0.04, times h, plus 3 times 0.2, 0.2 times h squared, plus h cubed, minus 0.2 cubed, so minus 0.008. Okay, all over h, and that's a long straight line here. So let me get my line drawing tool. Whoa, right? By the way, that's the result of doing this. 0.2 plus h times 0.2 plus h times 0.2 plus h. I just used the binomial distribution a little bit. I know the coefficients are 1, 3, 3, and 1. But you can FOIL this out, and then FOIL that out, or distribute that out, and get the same answer. All right, so the limit as h goes to 0 of all of that over h. All right, so notice something here, and this is really important. This should happen here whenever you do this, with a polynomial expression at least. Minus 0.8 and plus 0.8 cancels out, right? And we have an h in every term, so I can cancel an h out of every term. 1h, h squared becomes h cubed becomes h squared. Okay, and so this becomes the limit as h approaches 0 of let's see, 3 times 0.04, which is 0.12, okay, plus 3 times 0.2 is 0.6 h plus h squared. Okay, now we're taking the limit as h goes to 0. So as h goes to 0, this goes to 0, this goes to 0, and we end up with 0.12. Okay, let's check our tangent line here with Desmos again and see if we get that's what we got. Okay, hopefully it is. All right, so we're letting h go smaller, 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 smaller. 0.14, so I'm reading the answer down here. 0.14, 0.13, 0.13, 0.13, 0.12, 0.12. Now I can't get it to read exactly 0.12 because I can't let this go absolutely to 0 because 0 is undefined. Okay, but it's really close, right? And so the results I'm getting out is kind of like the table method of taking a limit. And you can see hopefully that it does bear out with the fact that the limit actually is exactly 0.12. Now, something worth noting here, the slope, this is the slope, right? That is tangent. Okay, the slope that is perpendicular, or the slope of the normal line, is -1 over 0.12. Okay, and I won't reduce that or simplify that. You can turn it into a fraction, reduce it, and flip it, and all of that stuff here. Okay, but that's the slope of the normal line. And you're going to be asked probably to write the equations of lines, so you do need to remember your point slope formula. Y minus the y value equals mx minus the x value. All right, hopefully that helps. And you're going to learn a lot more in the lesson, of course.